So today we'll continue talking about selected topics, and what we're going to talk about today is salt fluxes. And you might ask, why do we talk about salt fluxes? And does anybody have any idea why should we discuss salt fluxes in an estuary? It affects fish. Well, that's a good reason. What else? Right. So it gives us an idea of how efficient the estuary is to flush itself, and to how it is able to import salt and get rid of the salt. How efficient it is in that process. But by doing this, also we're able to use this approach to other tracers in an estuary. We know that salt is a conservative tracer. Other tracers that we might be interested in, like sediment, suspended sediment, or any type of organism that's floating in the water, or any pollutant. They're all tracers that we can determine how much is coming in from the ocean and going out from the estuary by determining this first the salt flux and then the quantity of interest. So the basic approach, or there's not much to say about it, but there could be a lot to say about it too. And we're going to start by showing that there's not much to say about salt flux because it's a straightforward calculation. But then again, there's a lot to say about it because by saying a lot and by looking at the salt flux in a lot of detail, we can know what mechanisms are the ones responsible for bringing salt in and out of the estuary. And as you will see, hopefully by the end of today, there are different processes in different estuaries that allow a tracer to go in and out of an estuary. So essentially, to determine the salt flux in an estuary, as illustrated in this diagram, you can subdivide a cross-section with different areas in the cross-section. So in this particular illustration, each individual element there, each square or almost square has a known area. So if you can determine what the flow is at each one of those squares, you just and the salinity at each one of those squares, you just multiply the flow times the salinity times the area of each square, and that will give you the total salt flux at that particular time. Right? So for that, you need simultaneous measurements of velocity, salinity, and the area. Well, you can generate a regular grid with your data, and with that you can determine the salt flux that's given by that expression. So that's the total salt going in or out of that cross-section at any particular time. So you can see that the concept is very simple, and we could say, okay, that's the way of determining salt flux. But doing it is not very easy because you can imagine the effort that requires to cover a cross-section with velocity and salinity measurements. How would you do it from what you've seen in this class and gone out on the field, and how would you do that? How would you determine the salt flux at a cross-section at any particular time?
Because usually in the CTDs, there are different locations where you average out, it's like a cross-section.
Yeah, so you're talking about doing CTD stations, right? And what else? So that'll give you the salinity, right? And what else? Right. So with the towed ADCP, you get profiles of velocity. The trick is that with the CTD, though, we don't get it enough, the same spatial resolution as we do with the ADCP. So that is a problem right there. So you can alternatively do CTDs as fast as you can as you move across, and that some people do that, and that'll give you enough spatial resolution. Also, an alternative is to tow flying vehicle or swimming vehicle in the water with a CTD. And we have one here, but we don't have a boat that is able to pull it from behind. So we can do that in the field. So hopefully in a in a year or two we'll be able to have that capability too. But you can see the difficulties of getting a reliable estimate. Alternatively, you can put a lot of moorings across to get the flow field, but also you need a lot of moorings to measure salinity across. So again, the concept is straightforward, simple, but getting a good value is not easy. I hope that you get that impression from here. So we said that through a relatively straightforward calculation, we can learn about relevant mechanisms responsible for transport of solutes or any tracer. So when we talk about salinity, think about your favorite tracer. It can be suspended sediment for those of you who are interested in sediments, or little phytoplankton organisms if you like plants, or zooplankton organisms if you like little animals, or any chemical tracer if you like pollution. Okay, so now that could be all that we could say about salt flux, but no, we're going to say more because we haven't seen how through a salt flux calculation we can determine the processes that cause the transport of the solute into or out of the estuary. So we're going to use several approaches. And one is, first we're going to use a spatial approach, and then a spatial and temporal approach to calculate salt fluxes. So in order to do that, we're going to use some definitions here as represented here. So whenever we use an overbar in this class, today's class, an overbar will represent a sectional average at any given time. So at a particular time, an overbar will represent the sectional mean, and a prime will denote the deviations from that sectional mean. Okay, so the overbar and the prime have a spatial context. And then a bracket and a tilde will have a temporal context where the brackets will represent tidal average, and the tilde will represent a tidal fluctuation, that is deviations from the temporal average, so tidal fluctuation. So keep this in mind. At the beginning, we're going to be only using overbar and prime. So we're going to talk first about the spatial context of the salt flux, and then we'll add the temporal context, okay? So let's see first in a little more detail how we can do the salt flux calculation. So the salinity and actual velocity at any point and at any given time on a cross-section of an estuary may be represented as the sum of a cross-sectional average plus the deviation from that average. So what that represents is that the axial flow could be given by the sectional mean plus the deviations from the sectional mean. Right? So this U bar would be the mean throughout this entire section. The S bar would be the average salinity throughout the entire section. And the primes would be the deviations at each one of these grid points from the sectional mean. So the U bar will be the same, and S bar will be the same for the entire cross section, but the U prime and S prime will be different for each one of the grid points. So we're talking an area A. So the integral over the entire cross section of the product U bar times S bar yields the rate of salt transport due to the mean flow. So the cross-sectional average flow. So that's the salt transport due to the cross-sectional average flow. The product of the cross-sectional average of U times cross-sectional average of S, that gives us the cross-sectional averaged flow or salt transport due to that flow. And it's simply that. Is that the whole story? Do I ask you? I mean, what are we missing from here? If we just do that, if we go and measure again, and measure a cross-section flow throughout the cross-section and salinity throughout the cross-section, and then get the cross-sectional average of the flow, the cross-sectional average of salinity, and multiply them, and then times the area of the cross-section. Is that the whole salt flux? No, right? Because we're missing the deviations from the mean. So that would be, perhaps that would be the largest contribution, as we will see in a minute. Perhaps that will be the largest contribution, but still, we're missing the fluctuations of U prime, S prime, the fluctuations, the deviations from the cross-sectional mean throughout the cross-section, at each one of these grid points of the cross-section. So that we call the shear dispersion. So that's given by the product of U prime times S prime throughout the cross-section. And if the flow is uniform throughout the cross-section, so the flow is the same throughout the cross-section, there are no lateral variations or vertical variations, then this U prime S prime will be 0. If there are a lot of shear, if there's a lot of lateral shear, then this term will become important. If there's a lot of vertical shear also. So the shear dispersion can have two flavors: the vertical shear dispersion and the transverse shear dispersion. So schematically, you can look at it that way: that a blob of salt will be dispersed by a sheared flow like that. So if we're looking at it in the vertical, like this is the vertical axis, and this is the horizontal axis. So if the flow is sheared like that, like any co-wet flow, then there will be more dispersion of the salt in these upper layers where the flow is strongest. So that's the vertical shear dispersion. And also, if instead now of this axis being the vertical axis, if it's the lateral axis, if the flow is sheared across, as in a channel versus a shoal, then you're going to have, again, more dispersion of the salt where the flow is strongest. Right? So that's the horizontal shear dispersion. So again, going back to the previous one, the mean salt transport, or the salt transport due to the mean flow, may contain most of the information regarding the salt flux, or the contribution to the salt flux may be dominated by the mean flow. That's as long as the lateral shears and vertical shears in the flow are weak. But if there are very strong shears, either in the horizontal or in the vertical direction, then this fluctuation term, this shear dispersion term, will be important for the salt flow. Right? So keep that in mind, because a lot of people tend to forget about these terms when they do calculations of fluxes, and they just take the one value, a representative value for the cross section, both of flow and of whatever tracer you want, sediment or pollutant or salt. So you have to be aware of these other terms. Right? So the shear dispersion can be looked at as a spatial covariance between the flow and the salinity. So this go back. It's a spatial covariance with respect. I'm sorry. These represent then fluctuations or deviations from the cross-sectional mean. So that's in the spatial context then. At any given time, the salt flux could be thought of as having two contributions, one from the mean flow and one from the sheared flow. Right. So now, let's include a temporal context to the salt flux calculation. In order to do that, I'm going to introduce a concept before we talk about the temporal context in the salt flux calculation. I'm introducing the tidal pumping concept. And the tidal pumping arises from the fact that with every flood you have salinity being advected into the estuary, and then it mixes, that salinity mixes with fresh water that's in the estuary, and then during ebb, lower salinity goes out. So in other words, tidal pumping is the pumping of salt with every flood period, and the export of lower salinity water with every ebb. So in essence, that's what tidal pumping is. It can be regarded also as the covariance of the salinity and the flow fields. So if they co-vary together, if there's a very straight relationship between the flow and the salinity, then the tidal pump, the salinity flows through due to tidal pumping will be large. Let's see if we can guess from this picture how effective the tidal pumping term will be. So here we have data of density, of water density, but it could be regarded as salinity also. This is at one of the tributaries to Chesapeake Bay. So we have depth versus time. So this is a full semi-diurnal tidal cycle. And underneath here we have depth versus time of the contours of flow. I think we've seen this example before. So you can see here that in red means ebb. So this entire period is the ebb period. This is the flood period. Or this is the end of ebb right here, beginning of ebb, the broken line. So you can see here that toward the end of ebb, you have the lowest salinity or lowest density, but the highest salinity or density occurs pretty close to when the highest flood is. So if you see during ebb, the salinity is sort of 90 degrees out of phase with the flow. So the minimum salinity, that is the extreme value of salinity in the low end, occurs pretty much at zero flow. And I will illustrate that in a moment. But during flood, you have that they're almost in phase, the maximum salinity almost with the maximum in flood. So there's a strong covariance during flood, but a 90-degree phase lag between flow and salinity during ebb. So in that case, the tidal pumping flux is important during flood, but not during ebb. In a simpler case, you'd have something like this. the salinity fluctuating with the tidal cycle like that, and the flow changing together with the salinity as you see here. The maximum salinity is achieved during maximum flood, and the minimum salinity during maximum ebb. Right? So in this case, you have a perfect covariance. They're in phase, both of them. So the flow and the salinity co-vary. So that means that in this situation, the tidal pumping mechanism to drive salinity in and out of the estuary is very effective. Okay? Can you think of a situation in which this may happen? I mean, in a typical estuary, they're 90 degrees out of phase. Typically, the maximum salinity will appear at the end of flood, and the minimum salinity will appear at the end of ebb. That is when the flow is zero. You'll get the extreme in salinity values. So in that situation, the tidal pumping term will be zero or very small. In the situation where you have a 90-degree phase lag between flow and salinity. But when they're in phase, like in this case, the tidal pumping mechanism is very effective. So this might happen in estuaries where the tidal wave is standing, because the salinity value the maximum salinity, the extreme in salinity will coincide will almost coincide with the extreme in flow also. So this is something that just through recent observations I've realized, but I haven't looked at carefully, and nobody has. So this is something that has to be explored, whether this is true that the tidal pumping mechanism dominates the salt flux. And I'm getting ahead of myself because I'm going to come back to this point at the end. Dominates the salt flux in systems where the tidal wave is standing. So keep that in mind, and I'll come back to it. So right now I'm just trying to introduce the tidal pumping effect. And so again, in this example, we have perfect covariance between the oscillations, the tidal oscillations of U and the tidal oscillations in salinity. So that's when you have the tidal pumping salt flux be effective. Okay, so again, this was to introduce the concept of tidal pumping. Now let's go back to see how we can include this temporal context in the salt flux to the overall salt flux calculation throughout the tidal cycle, say. But before including the temporal context, we're going to look at the spatial context first with a slightly different flavor, as we just saw a moment ago. So we'll call the the water transport, we call it Qi sub j, where I is, as you can see in this axis, refers to each row or to each depth, and j refers to each column here. So the transport of water will be given by the area of each one of these elements times the flow at each one of these elements. And the transport of salt will be equal to the area of each one of these elements times the flow at each one of those elements, that is the water transport, times the salinity at each one of those elements. So this is sort of repeating what we had seen before. So now we're going to do we can define blobs of depth and columns of water. So we'll start with blobs of horizontal layers. So we'll call U sub I would be the transverse mean at any depth I, and the UIT will be the sum of the flow at that depth. So this would be the integrated flow throughout that slab of water, U sub IT, and the A sub IT will be the area of that slab. This whole area. Okay, so with that we can define the transport through each transverse strip, that is the transport through each of these slabs will be given by the area of the slab times the flow that's integrated throughout that slab. That's the I sub I. And the salt flux will be that water transport times the salinity that also integrated throughout that slab. So with this gives us the water transport and the salt transport throughout this surface slab. You can do the same thing for each one of the slabs. And now we can do a vertical column that we'll call V sub j, as given here, and that's going to have an area of A sub Vj, which is this area, and we'll call U sub j the vertical or depth mean of this strip, and the UVj is the transport of this. So the transport through each column of water given by that strip will be the water transport is the area of that strip times the vertical average flow over there, and the salt flux will be again the water transport times the vertical average of the salinity of that strip. So you can calculate the salt flux by summing all these slabs or summing all the columns. At the end, you will get the same answer. So in general, we can call the rates of transport through the cross-section as represented by Q sub Vt, so the sum of all the vertical slabs and horizontal slab, and the salt flux given by that F sub Vt. So that's in terms of average. Now we're going to look at the deviations. The spatial deviations from the mean are given by these primes, which are the deviations are the flow at each one of these elements minus the sectional mean throughout the entire area. So these are deviations. These U prime represent deviations from the sectional mean. And then a difficult term that's called the interaction deviation is given by this U sub ij, which represents the flow at each one of the cells minus the cross-sectional mean plus the fluctuations with respect to the slabs and with respect to the water column. So this term will usually be a small term, as you can imagine, because we're looking at deviations from deviations. So in general, the rate of salt transport throughout the entire section is given by this representation. The area, this is the cross-sectional area, times, so this is the same representation as we showed at the beginning of this class, that it's the same as integrating the product of U times S throughout the cross-section. So it's, again, the cross-sectional area A sub VT, which is the same as this A that appears here, this A sub V sub T, multiplied times the Uij Sij. So that's it. That tells us the total salt transport throughout the section. Now let's see how we can find the different parts to this transport. So if we, instead of using Ui sub j and Si sub j, we use these representations where we have the water transport given by this and the salt transport given by that expression, and using the deviations and the interaction term, what we get is that the salt transport, this salt transport will be given by the water transport times the sectional mean of salinity. This is the sectional mean of salinity. So this is the water transport throughout the section, average throughout the section, times the salinity average. So again, let me go back. This is the same as when we were talking about a few minutes ago. This is obtained just from a cross-sectional average of U times the cross-sectional area. That gives us Q, so VT. And then the S bar is the cross-sectional average of salinity. Then this is the shear dispersion term, but we have the I's. The I's are the slabs, right? So this would be the vertical shear dispersion term, and this would be the horizontal shear dispersion term. So this is the same as we had defined before. This is the mean flow salt flux, or the salt flux due to the mean flow and salinity. This is the shear dispersion in the vertical, and this is the horizontal shear dispersion. And then we have this interaction term that has all these terms. Look at all that. The covariance here of the deviations of from the cross-sectional mean between the flow, the deviations with respect to the slab mean, and the deviations in salinity with respect to the column mean. And then here we have the fluctuations, the deviations of the flow from the column multiplied times the deviations of the salinity from the slab mean. So you can see all these terms are interaction terms, and you can see it gets rather obscure. But if you're able to follow through the calculation of these, you'll find that this term is really small. So it's almost useless to include it. I mean, its complication is not the complicated shape of that term makes that most people that use salt flux calculation ignore this completely. But in areas, I think that in areas where you have very large gradients in flow and in salinity, this might be a term that would be worth exploring. Okay? So again, that is a spatial representation at any given time. And this is something that we've talked about before, but we've just added this interaction term right now and written in a slightly different way than before. So it's at any given time. Now let's add the time variations. So we will define the tidal oscillation of the water transport as Q tilde, and it has zero average because it's a purely tidal fluctuation. It has zero average. And what we're going to get is that the cross-sectional mean of the water transport is given by temporal mean plus the tidal fluctuation. So that QBT represents cross-sectional mean. So think of the water going in and out of the inlets that we studied. So at any given time, well, rather throughout the tidal cycle, you can get, this one will be the average, the tidal average of all the water that went either in or out. So say in Panama City, in St. Andrew Bay, which has clearly an addition of water from the river there. This will be into or out of the estuary here. These Q's of BT. It's out, right? Because we're adding water from the river. So this QVT will represent one value in cubic meters per second. That represents how much volume of water is going out. Volume per unit time. So that would be it. And then this would represent the tidal oscillation, how large the tidal oscillations were. So what do you expect which term to be larger? The mean flow, this tidal mean flow, or the tidal oscillation? So with every tidal cycle, you have the volume that goes in and out. Is it larger or smaller than the net volume that goes out in the case of Panama City? What do you think? Is the mean flow larger or smaller relative to the tidal flow? Which is larger, the tidal flow or the mean flow? The tidal flow. So this has to be larger, just this QV, this of PT. So this represents the tidal variations of the water transport through the inlet. And in the same way, the salinity is given by a cross-sectional mean and temporal mean. So keep this in mind, that these give us one value only, and that represents the cross-sectional mean and temporal mean. So it's the average in space and in time. These two. This is the mean water transport in space and in time, and this is the mean salinity across the inlet and throughout the tidal cycle. And this is the amplitude of the salinity throughout the tidal oscillation. So if we add this temporal variability, and we're not going to go through it, but what we get is we get all these terms. And this is the bottom line, really, of this whole class. So this is where you wake up and start trying to understand what's going on here. So this is the salt flux, and we have one part that's caused by the residual flow, which is given by this expression. So again, that's the cross-sectional average of the water transport averaged over the tidal cycle. So that gives you one value. Right? So we had 30 repetitions of that transect. So for each repetition, we get one value of cubic meters per second going in and out of that inlet, right? So the average value will be the cross-sectional average for it. And then you average the 30 repetitions that we did, and you get that value. Same with salinity. We didn't cover the inlet enough, we just had one CTD cast. But if we assume that the average value of salinity of that CTD is the cross-sectional average, then get that value, we have how many casts at that station at the mouth? We did 30 repetitions, so it was like 15 casts, I think. So you'll get 15 values of salinity of, let's call it cross-sectional average salinity. So those 15 values, you average them, and you get one value. So the product of those two will give you the residual flux of salt. And typically, in most applications, that's the one that's going to dominate the salt flux. The next is from tidal pumping. And Here it is. It's a covariance between the transport and the salinity. So these are tidal variations of water transport and salinity averaged throughout the tidal cycle. So you can see here, these are variations with respect to the temporal mean only. So these are tidal variations of salinity and tidal variations of water. So notice that the temporal average is calculated from the product, not from the separate contribution of Q tilde and S tilde. It has to be Q tilde times S tilde average. So in other words, it's a covariance within the tidal cycle of this water transport with the salt transport. And again, if you remember what we said, it's that when they're in phase, in perfect phase, this term will be very large. So in most estuaries, these are not in phase, so this will be a relatively small term. Sometimes when it's large, it's 10 or 20% of the total salt flow. And then you have these terms that we have paid very little attention throughout the years, and people have just disregard them. They say that they're too small. But again, I would insist that in regions where you have large shears, horizontally and vertically, you might find that these are important. So you have the vertical shear dispersion, which is this term, and the transverse shear dispersion. And then you have the interaction between vertical and transverse deviation. So this would be eddies that are transporting salt and that have both a horizontal and a vertical structure. That would be salt transport by that. So reviewing this salt transport is produced by the estuarine circulation, the net flow. So that's the residual transport. And then the tidal pumping transport will be produced by how the salinity is related to the flow. If they're in quadrature, that is 90 degrees out of phase, then it'll be 0. If they're in phase, then the tidal pumping term will be large. And it's how the salt field is related to tidal variations. Then you have the shear dispersion terms. So in areas of large lateral shear or vertical shear, you're going to have some salt transport produced by these mechanisms. And then the interaction term, that would be in areas where you have that the lateral shears and the vertical shears are related by the same process. And they're large enough to transport salt. In general, that term is small too. So most of the times you'll see that you can express the salt transport by this term only. So all that we have said, just for that, for this to be the most important, typically. But again, it's always useful if you have the data. First, it's hard to get the data to be able to do these calculations. But then if you have the data, it's useful to go through these calculations and so that you know what the mechanism responsible for salt transport is. And I will insist that in most cases, people have found that this is the main mechanism. In some cases, this can be important. And again, I'll bring this up again. I would argue that in systems where the tidal wave is standing, this might be the most important mechanism. This is an idea. I wouldn't call it a hypothesis. It's an idea that might be worth exploring. And this is just from a couple of examples that I've seen, and I'll show you one of them. And then these terms could be important, but people have neglected them in general. But again, they could be important where the transverse and vertical shears are important. I'm sure that this will be very small in most estuaries. Okay, so this same relationship applies for sediment transport. There's an example of how it was applied for sediment transport. And for ceston transport, does anybody know what ceston is? No? Does everybody know what nekton? Huh? Nekton is not plankton. Nekton is whatever swims in the water. That's the nekton. And ceston has to do with plankton too. But I don't remember what ceston is.
You don't know either?
Huh? I don't know either. But if you told me, I know what it is. But it's because it's a particular type of plankton, and I don't remember. I couldn't tell you which. I know that it's not nekton because nekton swims, and ceston is at the mercy of the currents. Nekton is not. Ceston is at the mercy of the current, at least during a particular stage in their life. So you can look at the most recent reference on salt flux, in which they try to unify all the approaches to calculate salt flux, appears in that paper. So let me give you an example of salt flux dominated by tidal pumping, at least at one location. This is an interesting example. So this is, where are we here? Remember, I've shown you this area a couple of times before. Does anybody remember? No? No idea where on earth we are? Yeah, this is Argentina right here. This is Chile. So this is the Strait of Magellan. You've heard of the Strait of Magellan, right?
It's dangerous.
It is dangerous. Yeah, the currents are strong here. If you go to Antarctica, most probably, if you go to Antarctica via South America, most probably you'll get the ship right here and then sail out here and then go south. Okay, so I'm going to show you some data from a nice fjord there. There's a fjord, and it's a glacier fjord. A glacier is here, and the bathymetry of the orange line is orange line. That's the bathymetry. So this part of this transect is here, and this part of the transect is here. So notice this very shallow sill, that it almost gets all the way to the surface. The depth is 2 meters at low tide of that sill. So it almost effectively is isolating this basin from that basin. This hill is located right here. And I'm going to show you data from this line right here, this red line, without including the triangle here, just the line. So I'm going to show you some a representation of flow and salinity as a function of distance and time. So in the representation, this part of the transect will be on your right, and this part of the transect will be on the left. Oh, we're not there yet. So this is a cross section, just so that you see what how salt could get into the basin. So again, we have the seal, the shallow seal that is here, and just to keep you awake, I've changed the orientation of the figure. There's the seal, and this part of the figure is now here, and this part of the figure is over here. Okay, so this is the basin, this basin that's insulated from by the seal. So we have here salinity, temperature, and density. And you have a lens of fresh water that's also cold. Notice the salinity is around 22 at the surface and around 30 at the bottom. Notice that the lens is very thin, less than 5 meters deep, and it coincides with the temperature signal. So it's cold water on top of warm water. How's that possible? The salinity dominates. And why is it that it's cold at the surface? Because it's water from the glacier. Water that melts from the glacier. It's buoyant and it goes to the surface. Buoyant because it's fresh. Okay, so you can see that the outflow layer, the layer of fresh water, is occupying almost the entire water column over the seal. Right, so you have a net outflow right there. So the mean flow will not bring salinity into this basin. If you can imagine that, the mean flow will collide against this wall and cannot transport over the seal into this basin because the mean flow at the surface is out. So the mean flow is exporting fresh water away. So how is it that we get high salinity water there? Huh? Well, that's a good explanation. But if I tell you that it's not anoxic, that would be the explanation. If that's the explanation, then this basin would be anoxic. And it's not anoxic. Right. So here's the question again. I'm telling you that the mean flow, the tidally average flow, right here over the seal is out. So there's no way that the mean flow can put salt into the basin. So how can you get salt into the basin? With every tidal cycle, there's going to be flow over the seal into the basin. When there's flood, you have salt being transported in and pumping salt with each flood. So pumping, that's why it's called salt tidal pumping, because with every flood you're pumping salt in. So this is a place where you have the dominance of tidal pumping. There's no way that the mean flow can transport salt into the system. So here's the representation I was telling you about. So, oh, come on. How I did it. I'm gonna do it. No, it's not going to show me that. So this side of the plot is toward the ocean, and this side of the plot is toward the basin. So we have distance here, and we have time. So look at this panel first. So, and this is the colors are surface salinity. I give it as given by this color palette. So this is fresh water that comes out, and the seal is right around here at minus 0.2. No, sorry, actually it is right here at minus 0.35 distance. So this is where the seal is. So you see during ebb you have water going away from the basin into the fjord toward the Strait of Magellan. During flood we have salty water intruding. You see that the flood is sort of irregular. It's a fascinating area because you have these short wave-like pulses. It's not a 12-hour pulse, but it's more, the tide gets distorted. And I'm going to use this example again when we talk about tidal distortion. Because you see these blobs every 3 or 4 hours of high salinity water. Obviously the highest excursion was here with the strongest flood. But anyway, the point here is that this is how salt gets pumped into the system with every flood. All right, so that's just to illustrate how salinity gets in. But now here, let's look at the phase of the salinity, which is the red line, and the phase of the flow. So notice how the flow and salinity are in very different phase on either side of the seal, and right over the seal they're sort of in phase. So if you calculate the salt flux, the total salt flux, which is the continuous line, U times S, and And then if you calculate the salt flux produced by the mean flow, that's the dashed line, and the tidal pumping salt flux, which is the tidal variations, the covariance between the tidal flow and the salinity tidal oscillations. What you get, and these are all averaged throughout the tidal cycle, what you get as a function of space is what follows. You can see that the total flux, which is the continuous line, is followed very closely by the dotted line, which is the tidal pumping, except here. So you can see that here over the seal and over this area also, the total salt flux is explained by the tidal pumping mechanism. Whereas right here, well, right here it's closer. From here to here, the total salt flux is explained by the mean flow salt flux. So what happens is that right over the seal, because of I'll give this example later on also. Over the seal, there's a complicated interaction between the flow and the seal, and that makes some sort of a standing wave at the seal. So the standing wave nature, the standing tide nature at the seal makes the covariance between the salinity, the tidal covariance between salinity and flow to be large. That is, the salinity and flow become in phase here, right in this area. And they're 90 degrees out of phase in this area. So over very short distances, you can have these dramatic changes. So the point here is that in the region of the seal where you have a standing tide, where the flow and the salinity become in phase with each other, as you can see here, close to being in phase. And then the tidal pumping mechanism is the most effective in driving the salt into the fjord. What this means is what we said conceptually, that with every flood you have pumping of water, pumping of salt into the system, and that the mean flow cannot bring salt into the system because it's not at the depth in which it can override the seal. So in essence, that's what this plot is showing. And an idea that would be interesting to explore, not for this class anymore, but because we don't have the data to be able to do it, but the idea that these and another system, a coastal lagoon in Mexico has suggested, is that in systems where the tidal wave is standing, the tidal pumping mechanism is important. It's more important than the residual, than the mean flow mechanism. Okay? So that's it. Don't forget to send your